What I have sitting here on the bench is a Sencore cable TV video signal analyzer. It's called a VSA794. Here's a picture of it from the catalog, the original catalog. And you notice the screen there is lit up with a kind of yellow, the graticule, and then it shows a video waveform behind it. What these units were used for is for testing old analog cable signals, the video signal for an analog TV, and they're pretty much obsolete today. But what I really wanted to show is the one of the common problems with this. And if you want to fix one of these up, they're still useful for looking at NTSC signals. And by the way, there's a similar unit to this one that's the CVA94. You may notice that's a 794 and this is a 94. They're basically the same unit. The difference is this one is optimized for working on video cameras that produce NTSC signals, whereas this is for working on or analyzing the video from a cable system. But it's basically the same signal, has basically the same functions. But one of the big problems with this line of equipment was in that graticule illumination system. And so I want to show you what generally happens to them and how you can fix it. To do that, I'm going to have to take this front bezel off, which basically involves removing all the screws around the outside edges. I think there's 2 on each side, 3 on the top, 3 on the bottom. So let me do that, and then I'll come back and show you what that'll allow you to do. Okay, now I've removed all of the screws around the outside of this bezel. I've also removed the pull-out chart, which I'll show you here. The way this thing works is those little tabs slide in. It goes in this way, and when they slide in this this holder on the bottom, and then those little tabs catch behind here. So to take it out, you just need something kind of flat to press those down so that you can pull them out. Table knife works pretty well. So does a putty knife. Anything that's kind of a flat, thin blade. Okay, so let's see if we can get this this bezel off now. Pull this up here. Here. Okay. And now I'm going to stop the camera for a second to set this unit down. And then we're going to try to remove the... okay, I've laid it down and I've loosened the top cover a little bit. It just fits into these little slots on the side over here and in the back. Turn on a little more light back there so you can see some little plastic fingers back in the very back there, and this slides over the top of those fingers and fits in that slide as well. So having removed the top, you can now get to a number of things, some of which include this little board right there. I'm talking about this board right here that mounts with these 2 screws. That's the Illumination Board. So I'm going to take that out next, and I've already replaced the bulbs. Let me see if I can find one of the bulbs that came out of it. Yeah, this is what they look like. They're incandescent 12-volt bulbs, and in a minute I'll talk about the design of this particular thing, because I'm not sure what the engineer was thinking about when he or she designed this particular method. But at any rate, well, let's take that board out and then I'll talk about it. Okay, I've taken the 2 screws out, and now I'm going to remove the board. And you see, this one, I've replaced those little incandescent bulbs with LEDs, and then I put a little series resistor here to limit the current. The reason is, of course, the forward drop on these are only about 2 volts, and the supply that this plugs into, which is that plug right down here with the little blue and white wires on it, runs about 35 to 40 volts. And without a resistor in there, basically the way that the system works with the incandescent bulbs is there are 5 of these in parallel, and so they draw a fair amount of current, and they draw enough current that due to the internal impedance of the power supply, it pulls the power supply voltage down to around 12 to 15 volts. The trouble is that when one of these burns out, the voltage on the rest goes up. So then the next one burns out, and the voltage goes up higher. So then the third one burns out, and then it's really high, and the fourth one burns out, and the fifth one burns out. And it doesn't take long when one goes. It's only a matter of time, and sometimes not very much time, until they all are gone. It's sort of a system that's designed to either work or fail completely. So you don't get partial illumination. As one fails, in a short period of time, the second one will fail. Sometimes it'll take a few days or a week. Third one will usually fail within a day, fourth one within hours, and the fifth one will go almost right away. So what I've done is I've replaced them with LEDs, and I've put in that current limiting resistor. The idea being to provide the illumination, but to have something that will last a little longer. Because without the graticule illumination, you really can't read the face of this. And the reason is, and I'll show you on this one, that graticule has all that information on it. The waveform appears behind it, but basically everything, and I'll show you how this works here in a little bit, everything from measuring the video waveform to using the vector scope features depend on being able to see that graticule. Well, as you can tell, I'll block off the light coming in from back. When this is just sitting there, it's almost impossible to read, and when there's any ambient light on it, like this, it's impossible to read. So you need that backlight, and I just used some ordinary yellow LEDs and like I say, a resistor. So the big thing now is I'm going to try to optimize that resistor to provide the most illumination without overloading the LEDs or the power supply.